That was after. Yeah.
Okay, folks, let's go ahead and get started. The very first thing I wanted to mention is don't forget this week, every single group is supposed to meet with me. We are going over your service learning project, what you have turned in, because the final edits are due in a couple of weeks. And so that way you know what needs to be altered, or we can discuss, for example, the science and what of the science needs to be changed, stuff of that nature. To sign up for a time, I've got to go in and update Thursday, but past that, if you look at your Blackboard under last week's folder, there is a link to two different calendars, one in the daytime and one in the evening. You need to click on the link to see if the time is available. Thursday, I know as right now I have, and if your group wants to catch it real quick, that's up to you. I will be in my office from 8 to noon. So that is Thursday's time availability. Don't think I have any time in that evening. So, I will be posting the lab for tomorrow here in a little bit. The lab for tomorrow is a thermodynamics lab. Again, we have not gotten to that, so the pre-lab is not due. You will have to come prepared to do the laboratory, and I will be posting as soon as I can. I will create this week's folder, and I will post in this week's folder when that lab will be due, because it'll be due next week. What I expect to go over with you this week is today we are going to deal with molar solubility and the solubility product. We will also talk about the common ion effect. And basically, folks, the information that we're going over is very similar to stuff that we've already done. It's just, it's going to be applied to ionic compounds instead of acids and bases. It will not be as complex as the titration though. It'll be much simpler than the titration from many perspectives. I hope to finish up with everything about the solubility product today. And then on Wednesday, we will start thermodynamics. We will specifically be starting with a brief review of enthalpy, which was discussed in College Chemistry 1. We will then carry on to entropy and Gibbs free energy, which should get you to a large extent through the laboratory that you're doing tomorrow. So that is the goal for this week. Again, I will be a lot more explicit when I can create your folder for this week, which will hopefully be this afternoon. Any questions for me so far? Yes.
Do we have to do with you this week? Or next week?
It's this week.
Okay.
I mean, if we have to carry over into Monday of next week, that will be fine. But you don't want to delay too much because of when all the stuff is due.
I was just looking at your points, you only have 3 of them, so I thought that.
Some groups have already claimed them, so. Any other questions? Yes, I have a crazy schedule. Okay, if not, we are going to get started into today's information. I'm going to start by reminding you a little bit of things that you have already encountered. In College Chemistry 1, I think it's around chapter 7 of our textbook, it talks about the solubility rules. And the solubility rules are specifically associated with ionic compounds. Ionic compounds being compounds that contain a metal cation. Now, under the solubility rules, we classify things as being soluble or insoluble based on those rules. Those rules are really generalizations. And basically what I mean by generalizations is, and I've used it this semester too, I've always said, if it has a group 1 metal cation, it's soluble all of the time. And for the most part, that is true. But it's definitely a generalization. And even though it's soluble all of the time, it doesn't mean that it's going to dissolve and dissolve and dissolve and dissolve and dissolve. At some point, it's going to reach a limitation. So back in College Chemistry 1, we classified those ionic compounds as soluble, meaning that they tended to be aqueous in water, or insoluble, meaning they tended to be solid in the presence of water. Now, since starting this semester, early in the semester, we started talking about solution formation. And one of the things we talked about with respect to solution formation is the solubility of solids. Now, we were focused more on what impacts the solubility of solids. And for the most part, again, this is a generalization. For the most part, as you increase the temperature, you're going to increase the solubility of solids in an aqueous solution. Now, what we're going to do is we're going to take these generalizations that we have been making, and we're going to get into more detail. We are going to talk about the molar solubility. This is going to be the molarity of solid that does dissolve in water. That's what the molar solubility is. It's the molarity of the solid that dissolves in water. We're also going to talk about the solubility product constant. The solubility product constant is better known as K subscript SP. And basically, the solubility product constant describes just how well does that ionic solid dissolve in water. Just like our previous discussions of equilibrium constants, the larger the equilibrium constant, in this case, the solubility product constant, the greater the amount the solid will dissolve in water. The smaller the solubility product constant, the less we would expect it to dissolve in water. Now, these two things are different. KSP will never change at a specific temperature. The only way to alter the equilibrium constant is to alter the temperature. But the molar solubility can change depending upon the environment that the solid is dissolved in. Okay, so let's just look at examples of these two concepts, the molar solubility and the solubility product constant. And to do so, we're going to look at calcium fluoride. Calcium fluoride, as a solid, is going to dissociate in water to form calcium ion and 2 fluoride ions. Now, just like we can look up an equilibrium constant for acetic acid, we can look up the equilibrium constant for calcium fluoride. We would look up the solubility product constant. And when we look up the solubility product constant for calcium fluoride, what we find is that the solubility constant for this, the KSP at room temperature essentially, is 1.46 times 10 to the minus 10. That solubility product constant, folks, is not going to change unless we alter the temperature of the water. So that is the solubility product constant. Now let's talk about the molar solubility. You're starting out initially with solid calcium fluoride. You have none of your calcium ion and none of your fluoride ion. As time progresses, the calcium fluoride is going to dissociate. And for every 1 calcium fluoride that dissociates, you're going to make 1 calcium ion and you are going to make 2 fluoride ions. Now, this number associated with this value, not the sign, but the actual number, that is going to be your molar solubility. So at equilibrium, you're still going to have solid calcium fluoride. We know this because the KSP is so small. But you're going to have made X amount of calcium ion and you're going to make 2X amount of fluoride ion. Any questions so far? Yes.
Could you remind me what you said about why it's 2x, is it just because of the stoichiometry?
It's because of the stoichiometry, because according to this, for every 1 calcium fluoride that dissociates, you make 2 fluoride ions. Folks, that is one of the first differences. When we were doing acid-base chemistry, and we were talking titrations, and we were talking anything else associated with acid-base chemistry, it always associated in a 1-to-1 ratio. When you're talking about an ionic compound, that's not going to be the case. When you're talking about an ionic compound, you're going to have to pay attention to the coefficients to figure out the ratio in which it dissociates. So that is number 1 difference. Number 2 difference is go ahead. This is even more important, I think, than it was with acid-base chemistry, and that is you need to write the equilibrium expression. If you write the equilibrium expression for this dissociation, the KSP is going to be equal to the calcium concentration times the fluoride concentration. And remember, when we wrote equilibrium expressions at the very beginning, it was always raised to their coefficient. So that fluoride concentration is going to be squared. Now, we're going to plug in the information we know. We know the KSP is 1.46 times 10 to the minus 10. That's going to equal the calcium concentration at equilibrium, which is X, and the fluoride concentration at equilibrium, which is 2x squared. So 1.46 times 10 to the minus 10 is equal to X times 4x squared. Or in other words, 1.46 times 10 to the minus 10 is equal to 4x cubed. Now I'm going to let somebody key that into their calculator because for some reason I did not bring mine, and tell me what x is equal to. Six 6.04 times 10 to the negative 6. Everybody agree? I don't think that's an x cubed. It doesn't feel right for x cubed.
Oh, yeah, no, I didn't do that. No.
So what else do you have?
3.3 times 10 to the negative 4.
That sounds right. Okay. So let's talk some differences compared to what you've been doing. Folks, when I bring up these differences, I'm also bringing up some of the most common mistakes. The number 1 difference I've already discussed, and that is when we're looking at equilibrium, or well, the change For every 1 calcium fluoride that dissociated, you made 1 calcium and you made 2 fluorides. You had to take that into account in their change. You had to take into account that stoichiometry in that change. So that's the first one. The second one, I see students all the time skip the next step, which is writing their equilibrium expression. Take that few seconds it takes to write that equilibrium expression. When you write the equilibrium expression, it is going to be the KSP is equal to the calcium times the fluoride squared. Again, you have to take into account that stoichiometry. Then you plug in what you have. The third thing I see students make. The third mistake I see students make. This 2, this square, means you got to square the 2 inside and the x inside the parentheses. A lot of times students just write it as 2x squared. Wrong. Try again. You got to square both things inside the parentheses. When you do so, then you get 4x cubed. So it would be 1.46 times 10 to the minus 10 divided by 4. And then you take the cube root of that. And for those that don't know how to take a cube root, basically you will take your answer to the 1/3, raised to the 1/3. And that's how you can take a cube root. Or I guess on a calculator, it would look more like raised to the 1/3. And that's how you take a cube root. Questions so far? Let's look at another example. Let's take lead chloride. Well, let's take silver chloride first. We're going to take silver chloride. Silver chloride, we were told, was an insoluble salt. Silver chloride dissociates to form silver ion and chloride ion. When you look up silver chloride in the book, you find that silver chloride has a equilibrium constant of 1.77 times 10 to the minus 10. Silver chloride is a solid. There is no silver and no chlorine at the start. As a change, we're going to lose X amount of silver chloride. We're going to gain X amount of silver and X amount of chloride. So that at equilibrium, you're still going to have solid silver chloride remaining, but you're going to have X amount of silver and X amount of chloride. The equilibrium expression for this is KSP is equal to the silver concentration times the chloride concentration, and both of these are raised to the power of 1 because they are in a 1-to-1 ratio. So the KSP, which is 1.77 times 10 to the minus 10, it's going to equal X times X, or in other words, the 1.77 times 10 to the minus 10 is equal to X squared. Taking the square root of that to get X, you get a value of 1.33 times 10 to the minus 5. when you are calculating these X's, folks, what you will see is the molar solubility. So what I want you to note is I gave you calcium fluoride with its equilibrium constant of 1.46 times 10 to the minus 10. And we found out that the molar solubility for calcium fluoride was 3.3 times 10 to the minus 4. And then we did silver chloride. Silver chloride has a value of 1.77 times 10 to the minus 10. And it has a molar solubility of 1.33 times 10 to the minus 5. What you will note is that calcium fluoride and silver chloride have similar equilibrium constants or solubility product constants. But calcium fluoride is more soluble. According to the molar solubility. Questions? When we were looking at those solubility rules, a lot of times we were comparing the molar solubility. Okay. So the next thing that I want to discuss is going to be the common ion effect. How many people had a chance to look at the group, the laboratory class data that I passed out on Wednesday of last week? If you did, what you would notice is that everyone or every group obtained a KSP of approximately equal to 0.001. It ranged really between 0.001 and 0.002. From what I just said, about molar solubility compared to equilibrium constants. Does that make sense? That everyone's KSP should have been about 0.001. No matter what environment you have. Yes, because what does the solubility product constant depend upon? Temperature. Were you all was all of your experiments done at the same temperature? Yes. So we would expect, and it was all the same compound. So we would expect the solubility product to all be about the same. What differed is the molar solubility. This, folks, was equal to, you did KHT. This was equal to the HT concentration, and it was equal to the K concentration. Well, no, we're not going to go with K concentration. It was equal to the HT concentration. What you would notice is that your molar solubility did differ. Now, the molar solubility differed because of the common ion effect. Okay. To get into this, I want you to start by thinking about Le Chatelier's principle. If I have simply silver chloride, let's see, y'all were doing KHT. I just got to keep in mind what you were working with. You had KHT solid dissociating to form K plus HT minus. We would expect if we threw solid KHT in water, which direction should this reaction head? Should head towards the products. Because you were adding a reactant. So you were driving the reaction towards the products. Now, other than one group in each lab section, you add KCl to this mixture. And KCl dissociates to form K plus Cl minus. So what you were adding is you were adding K plus. So we were added to our reaction equilibrium. We were adding a product that's going to cause the reaction to no longer be at equilibrium. So which way would the reaction have to shift to get to equilibrium? Back towards the reactants. If it's shifting back towards the reactants, that means we're going to have less HT. So I would expect if as the KCl concentration increased, or in other words, the K plus concentration before the reaction increased, you would have had less KHT dissolve. And that's because you're adding a common ion. So this is the idea conceptually. Let's actually look at it from a mathematical standpoint. You notice how a lot of these topics keep coming back? I think that's intentional, don't you? I want you to realize we're building on things you've already learned. Okay, so let's take lead chloride. Come on, pen. Lead chloride solid dissociates to form lead ion and 2 chloride ions. The KSP for lead chloride is 1.17 times 10 to the minus 5. Now, let's have this lead chloride dissolve in a, let's take this lead chloride and let's have it dissolve in 0.1 molar lead nitrate. Lead nitrate, according to our solubility rules, is a soluble salt because most nitrates are. So lead nitrate is going to dissociate entirely into lead ion and nitrate ion. You start out with your lead. Again, lead nitrate dissociates entirely. So you're going to use all of it up. So if we start out with 0.1 molar, we lose all of it. For every 1 lead nitrate that dissociates, we make 0.1 molar lead because it's in a 1-to-1 ratio. For every 1 lead nitrate that dissociates, you make 2 times that in nitrate. So what you really have in solution is you don't have lead nitrate, which is completely soluble. You have 0.1 lead and you have 0.2 nitrate. Now that lead nitrate is going to play a role in how much of our lead chloride can dissolve, because we're no longer starting out with 0 lead in our solution. Instead, we are starting out with solid lead chloride, but we're starting out with 0.1 molar lead ion and no chloride ion. As time progresses, you lose X amount of your lead chloride. For every 1 lead chloride that dissociates, you make 1 lead and you make 2 chlorides. So that at equilibrium, you're still going to have solid lead chloride left over, but you're going to have 0.1 plus X amount of lead, and you're going to have 2X amount of chloride. Writing our equilibrium expression, the KSP is equal to the lead concentration times the chloride concentration squared. The KSP was 1.17 times 10 to the minus 5. That's equal to the lead concentration of 0.1 plus X times the chloride concentration, which is 2X squared. Now, here is the next thing that is going to be different. When dealing with solubility products, you can ignore, or you can basically you can simplify the problem by ignoring the contribution of the solid if in the presence of a common ion. The reason you can do this comes back to that equilibrium constant. That equilibrium constant being so small says that the amount that's going to dissociate is really tiny. It's really tiny compared to the concentration of the common ion. So that means we can ignore the contribution of the solid in this equation. Therefore, simplifying this to be 1.17 times 10 to the minus 5 is equal to 0.1 times 4x squared, or 1.17 times 10 to the minus 5 is equal to 0.4x squared. So what did you get for an x? Zero 0.0017? Point 0054? So again, let's talk about this problem now that you got it all written down. A common ion effect will come into play when you take a solid and you dissolve it in a solution that has a common ion. Now, in this particular case, the lead nitrate because it does contain nitrate, is extremely soluble. It dissociates to form lead ion and nitrate ion. For every one lead nitrate that dissociates, you make one lead 2+ ion and 2 nitrate ions. So if we started out with 0.1 molar lead nitrate and none of our lead and none of our nitrate, then by the end, we're going to have 0.1 of our lead and 0.2 of our nitrate. This is due to stoichiometry. That lead concentration is going to impact the degree to which your solid can dissociate. So, and the way you do the calculation is you take your lead chloride and you allow it to dissociate. But instead of starting out with a 0 and 0, you start out with 0.1 molar lead 2+ from the common ion and 0 of the chloride. Then when it dissociates, again, this X is still your molar solubility. You make X amount of lead and 2X amount of chloride. So at equilibrium, you have solid lead chloride, you have 0.01 plus X amount of lead, and you have 2X of chloride. Plugging that into your KSP expression. The new piece from what we were discussing previously is that you can ignore, most of the time at least, you can ignore this contribution. And the reason you can ignore this contribution is because these numbers are so small. And that number, compared to that number, is so large. So when the common ion is much larger than the KSP, you can ignore that contribution, which simplifies the problem and allows you to solve. And one way you can check it is if you're not confident, you can ask yourself, is the molar solubility less than 5% of the concentration of the common ion? If yes, then the assumption is valid. If no, then the assumption is invalid. And you have to do the math without the without using the assumption. Okay, and in this case, it was less than 5%. So my assumption would have been valid. Well, less than or equal to 5%. Most of the time, it's going to be valid for KSP. So what I want to mention, one more thing on your post lab. So if I recall the post lab, the first couple of the questions related to the post lab is basically asking for you to understand the common ion effect. If there is a common ion, it is going to cause the amount of the solid that can dissociate to be less than expected. I believe some of the next questions ask you to look at that group data. And I've already talked about the group data and what that means. And then on the second page of the post lab, you are doing a problem where you are calculating the KSP of a solid. And if I recall correctly, it's a lot like the problem I just gave you. But basically what it says is lead chloride solid dissociates to form lead 2+ plus 2 chloride minus. When you write out the ice table, you would have solid, you would have none of the lead and none of the chloride. You would lose X amount of lead chloride. You would gain X amount of lead and 2X amount of the chloride. So at equilibrium, you have solid amount of lead chloride, X amount of lead, and 2X amount of chloride. It says then in one of the next problems that the chlorine concentration is, and it gives you a value, but let's say it's 0.005. Well, if you look at the KSP expression, the KSP expression is lead concentration times the chloride concentration squared, where the KSP is equal to X times 2X squared. Now, why I bring this up is because of this following fact. It says the chloride concentration is 0.005, and you just said the chloride concentration is 2X squared, or is 2X. So in other words, that 0.005 is equal to 2X. So X in this case would be 0.0025. So our KSP, if this were a real thing, would be 0.0025 times 0.005 squared. And then you would calculate. Now I just made up some numbers. So I'm not saying that's the correct value. But hopefully you see how to do it. Okay, with that, I will see you on Wednesday for thermodynamics.
Remember those sheets that were laying out here? This is Wednesday, Friday.
Yeah, and I didn't bring them with me. Well, I brought, the only thing I brought with me were these sheets.
Well, I have them.
Oh, you don't have to turn them in, no. These are due the week after Thanksgiving, I think.
Okay, I just didn't know if it was due yesterday.
No, it's not due until later.
I wanted to sign a tenancy and bring it to you. And I also wanted to ask me and my lab partner for Ada Arts, not lab partner, like group group project partner. We saw that you had messaged us in the group me saying that like our rank sheet wasn't done, all that stuff. When we had discussed it with our third member, the last one to drop. We were under the impression that she was doing it. We met up and completed our rant worksheet and aligned the two other worksheets. But obviously it was like past the deadline, but I was wondering, like, since we thought the other teammate was doing it and we were aware she had dropped or not completed
Send
it
it.
until you messaged us, is it okay if we get an extension on that?
Send me an email with the document
Yes, ma'am.
before we meet as a group.
Yes, ma'am. I think we're scheduled to meet this Wednesday.
Okay.
You have a secret meeting queue anytime after 12 days today. We have a question on the number.
I will be in my office from 1 till 4 today.
Perfect. Okay. I'll just stop by. Thank you.
I just needed to come see you today about my homework.
I'll be in my office from 1 to 4 today.
Okay, hopefully I can catch you in my lab at 3.
I'll be in my office from 1 to 4 today.
Okay.